Yeah. Okay, welcome to the Summer School on Model Predictive Control and Reinforcement by Joschka Bödecker and Moritz Diehl, myself. And we want to briefly outline what's the aim of this course. The aim is actually to understand the concepts of model predictive control, which is a well-known control technique, and reinforcement learning, a successful technique in machine learning. And our aim is actually to learn from each other. Joschka and I had this idea to give the course because we wanted to basically learn what the other side does. Joschka is an expert on reinforcement learning. He is a professor of neurorobotics at the University of Freiburg, and I'm an expert in algorithms for model predictive control. And what we also want to do is we want to apply these methods to practical problems, like invented smaller examples, possibly bigger ones in the projects. And for this aim, we do hands-on exercises in Python, which will be a very large part of the course and very important. The agenda is quite full. I will not zoom into this now. You find that on our webpage. But I want to point out that we will have every morning 2 lectures and then an exercise. Then we have a lunch break. At 2 o'clock, we start again. So we stick to this 2 o'clock starting time. And then we will have 2 another lectures and another exercise. In between, there will be coffee breaks for the real people here and for the virtual people in their own offices or homes, wherever they are. So you are welcome to join maybe together to drink your coffee together with others. And what I also want to say is that in the second week, we will have 2 guest lectures, one who is more from the field of MPC, Sebastian Gros, from NTNU in Norway, in Trondheim. And the other, Sergey Levine from Berkeley, who is an expert in guided policy search and other techniques in reinforcement learning. We are very happy that both agreed to join us, and they will join us virtually, so you will see them as remote people. I should also say that in the second week, we have dedicated lots of time for project work. So this is not for all participants, only those that want to do the project, which I really recommend to deepen the course. And this project is a very exciting thing, I think. It's most exciting for me because it is the chance for you to invent a problem that is hopefully related to your interest, to your research that you might do as a PhD student or as a master's student. And you formulate a small, tiny version, let's say, of the big thing that you're really interested in into a problem that is related to this course, and you work on it together with the tutors and with me and with Joschka. Yeah, we will really interact, and the exciting part, what I like about it, is that we will learn about your research in these projects. So you can start already thinking now what you want to do as a project. Yeah, so that's one recommendation. The team consists of, as we said, experts in both fields, in MPC and in reinforcement learning. We have already introduced the 2 professors, but I want to also introduce Katrin Baumgartner, who is the tutor and also main organizer of the location, the main tutor for, in particular, the MPC part, and Jasper Hoffmann, the main tutor for the reinforcement learning part. And I mentioned already the 2 guest lecturers, Sebastian Gros and Sergey Levine. I'm really looking forward to their talks as well, which are next Monday and next Tuesday. Yeah, Joschka and I thought that we would do it a bit interactive now, and Joschka will actually now ask a few questions, and afterwards we stop the recording, and then everyone is encouraged to switch on their camera, and then we will have a joint discussion on several questions that are related to the field before we actually start telling you anything about it. Okay?
Exactly. So we were interested in what you already know about these topics, right? We want to see a little bit what background you have and what you already, maybe you've had some chance already to work with these methods and what you've applied them with, and in general, your knowledge on these topics. So in particular, what do you know about model predictive control? What are characteristics of reinforcement learning that you know about? And maybe some differences to supervised learning that you may already know, yeah, just to compare this a little bit. So these are the questions we would like to discuss with you a little bit. And for that, we will stop the recording for now.
Good. Isn't, yeah. Mm-hmm. Okay, so Joschka and I did chat a bit before the talk, of course, and we tried to find out more about the similarities and what's different. And generally, MPC and reinforcement learning are both frameworks to solve sequential decision-making problems, obviously, right? Yeah, there's... Yes, sorry, I raised my voice. Okay, so both are methods to solve sequential decision problems, or control problems, as you could also call them. And both automatically design a controller based on just desired outcomes. So we just say what we want, like respect some constraints, follow some set points, and so on, in terms of stage cost and constraints. And then something that's obvious but important in particular for reinforcement learning is that closed loop system. That means the system after we control it visits of course different portions of the state space. You could also say a controller changes the behavior of a system, right? You can make an unstable system stable by a controller, and that's exactly why we like controllers, but it also poses questions for adaptation and learning. So let me start with the left side. What is MPC and what's a bit different to RL? I mentioned already that system identification is typically the first step. So you start with modeling, thinking, modeling your system, and then typically doing an identification campaign where you identify data based on, you record a lot of data and then you fit models to it. You then tune your MPC and only implement it afterwards. Also, one thing that's really interesting to know in practice, MPC people usually formulate convex objective functions. You know? The model might be nonlinear, but the objective is very often convex, like a quadratic deviation from a desired set point, penalties for going beyond some boundaries, and so on. And then we also impose constraints explicitly. That's a very particular feature in MPC, which is different to the practice of RL as it is now, that you explicitly impose these constraints all the time. So you solve optimization problems with constraints. And then the main part is that there is online optimization. So you do an online optimization over prediction horizon. So you predict into the future, and only for the current state and the current predictions you solve an optimization problem. This might be expensive online. That's one particular reason why MPC started in the process industry, where timescales are slow and the processes are very expensive, yeah, like chemical reactions, distillation columns. That's used since about 3 to 4 decades. And then I should also say that it's usually combined with some form of state estimation. So we have in control generally this distinction between a state and a measured quantity, which is sometimes a bit differently seen in RL, but I think we will clarify the differences during the first lecture on simulation and models. Now I give the word to Joschka, who will basically comment on the same points on the RL side, which I think show already some of the interesting differences.
Yeah, thank you. Right, so in reinforcement learning, we learn directly from data. This was already mentioned before also. Through trial and error, we don't have a system model available from the get-go. Moritz was mentioning system identification. This is also sometimes done explicitly in reinforcement learning, in the so-called model-based reinforcement learning setting, but often also you don't really learn an explicit dynamics model. You learn in a model-free way, and that's something we will explain and explore in the course, of course. And we already talked a little bit about the exploration-exploitation trade-off that you have to do. If you don't know your system, you have to gather information and then you have to act on it. In RL, we do have shaped or concave rewards. Yeah? So that's similar to the convex stage cost that Moritz was mentioning, but it's also very common to have very sparse 0-1 rewards, that you specify a goal region, for instance, where you would give a positive reward, but everything else is just 0. So these are typically rather hard exploration problems where the agent needs to roam around for a long time and maybe just receives 0 as a feedback the whole time. And only occasionally it will randomly stumble into the goal, if you like, and it will be rewarded, and it has to learn from those episodes. And this is it's a hard problem, and there are some nice ideas about that, but it's also an open research problem, how to best deal with these sparse reward settings. But in general, RL is doing both, I would say, these shaped rewards and these sparse rewards. We also have constraints in reinforcement learning, but usually we impose them via penalties in the reward function. That's the most common case, and they're not explicitly formulated like in the MPC setting. Yeah? So it's, you usually have reward functions where you have different terms that you need to weigh together in a way that makes sense for the problem, and that's not always easy. I mean, it can be quite difficult to come up with the best weights for a given problem so that you get the outcome that you really desire. We often have parameterized controllers. So we do have an explicit representation of our controller that has parameters. So for instance, a neural network, right? We could have a deep neural network as a controller and directly optimize its parameters based on the objective. And a difference to what Moritz explained about MPC is that usually the training is expensive for reinforcement learning problems, but the execution is comparatively fast. Yeah? So we just have to do inference with a neural network, for instance, in order to execute an action that we basically amortize the optimization process into this policy, if you like, during training. Yeah? And so execution is really fast. Right. We don't usually deal with state estimation. There is a formulation of reinforcement learning problems also that considers this case when we don't have perfect information and only partial observability, for instance. But I would say in most of the cases, it's considered to deal with problems that actually fulfill the Markov property, and we'll get back to what that means, so that we have full state information that we can act on, and nothing else matters for our control problem. And if this is not the case, we usually include some history into the definition of our state variables in order to get close to this condition. Okay. Other questions maybe to these points for now, before we go on? Yeah. Yeah. Mm-hmm. Mm-hmm. Okay, so for the online people, I repeat the question real quick. The question was, don't you usually in reinforcement learning also have a transition function, right? And wouldn't that be considered a model? And you would be right. I mean, it would be considered a model, but usually in the model-free reinforcement learning case, you exactly do not have that model. So you need to basically, and you also don't build it explicitly. You just interact with the environment, and you learn something that we call a Q function or Q factors. And that basically incorporates this information without having an explicit dynamics model. But as I mentioned, you can also do model-based reinforcement learning. That would be much closer to what Moritz described, where you have a system identification phase, and you try to identify this kind of a transition model from your data. Yeah? And then you do planning. Yeah, thanks.
Yeah, I suggest we continue directly. And I just want to say that we are building on a long history, and as many things in engineering and computer science, this competition, so to say, between MPC and RL, as we might look at it with a friendly competition in mind, nowadays is old, and it started in the 40s and 50s. Yeah? And let's say on the MPC side, I would see MPC, model predictive control, to be in a tradition. Maybe you might find that a bit surprising, but I would see it in the tradition of linear programming. And the reason is that linear programming was a technique used and developed to solve actually planning and decision problems early on in the Second World War, mostly like logistics problems, how many tanks should go from what location to what other location, and many other applications later. And it was then morphed into other techniques, for example, quadratic programming, nonlinear programming, integer programming, all this was building on it. You see it in the names. And what we nowadays call the mathematical optimization field is basically originating in linear programming. That's really when it took off. It was actually optimization of a linear objective with linear inequality constraints. And that is, so to say, the path that MPC is building on. And now, as said already, MPC is based on online solution of such problems, sometimes also integer programs, very often nonlinear programs, most commonly quadratic programs nowadays in MPC practice. So similarly, dynamic programming is building on reinforcement learning is building on another history, and that's maybe my personal view. You might correct it a bit in a minute, but Richard Bellman is surely one of the fathers, so to say, of this stream of research. I sometimes call it also state space-based techniques, dynamic programming, and there was this beautiful book from 1957, which contains already so many ideas which are still used nowadays and which contains already very similar language that I can really recommend you to look at it. Richard Bellman, Dynamic Programming, 1957. And what I found interesting is maybe a mini quote from this preface of the book in 2010, which was slightly before the advent of, let's say, of the deep neural networks, yeah, right? But it was when things started to become interesting already, and so temporal difference reinforcement learning is mentioned in this preface by Stuart Dreyfus, who was a collaborator of Richard Bellman. And I found an interesting quote that I just want to read for you. He was on this dynamic programming side. I developed this beautiful algorithm of dynamic programming, as we will outline tomorrow in more detail, and many of you know already. While Danzig had this linear programming on the other side, and they indeed were competing at that time already. And he said, despite our best efforts, however, surveys of applied practitioners in our area regularly and painfully for us showed dynamic programming to be used much less than our planning competitor, linear programming. So they obviously had a competition. So in that sense, it's not completely far-fetched to look at it from this point. Dynamic programming obviously developed into a much richer field, in particular under the guidance of computer scientists in machine learning. And I think I better give the word to Joschka to comment on the right side.
Thank you. Yeah, so absolutely right that dynamic programming is at the heart of these algorithms that we look at in reinforcement learning. And I think what reinforcement learning then brought additionally to the table was the ideas of how to deal with the case when you don't have the model, right? When you want to do dynamic programming or approximate dynamic programming without having access to a model, so by learning through sampling, right? And how to still be able to generate approximately optimal policies as you go along, as you train the agent. And then, of course, in the last few years, through the advent of deep learning, we've seen an explosion of application of reinforcement learning methods, where we're now able to deal with much larger state and action spaces than we were able to do beforehand, through the use of deep neural networks as function approximators and so on, as we'll see in the course also. Yep.
Should we look at the applications?
Yeah.
Just to give some ideas.
Exactly.
Maybe we skip some, but you start.
Okay, great. Yeah, so we want to whet your appetite a little bit, and we've selected some applications here. Let me see. Okay. Yeah. Okay, so here we go. I'm just going to do this full screen. So let me pause this for a second. Sorry. Usually you can control this, and then let me just go back and I'll explain a little bit what you see in the next video. So this is a video that shows reinforcement learning directly from pixel input. And it was really a milestone and a breakthrough in the reinforcement learning literature, where some folks from DeepMind, Google DeepMind, were able to, for the first time, train on these very high dimensional inputs directly from pixels. So these are old Atari games, from a Atari 2600 emulator, and the agent has to solve different games in this Atari simulator while not really knowing anything about the game dynamics. All it sees is the pixels, and it has to control the game somehow, and its objective is to increase its score. That's basically what they told, so to speak, to the agent. And I mean, if you think about this, doing this explicitly, doing control in pixel space, this wouldn't really be feasible. Yeah. So even though these are rather low dimensional pictures, something like 84 by 84 pixels with 256 gray values, still this is it's a huge possible amount of combinations that you could see, and doing directly control on that is not feasible. So what they did was to use deep neural networks in order to extract state information that they could then do the control, the learning on. And what you will see is, right. Okay, here we go. This is the training process. In the beginning, so this is breakout. You have this little paddle, and you have to try to bounce it back to the little bricks up there, and you get score points if you do that. And in the beginning, the agent doesn't know what to do. It doesn't know about the paddle. It doesn't know about the ball. It has to figure that out from the input images that it gets. And over time, you can see it develops a little bit better strategies to actually catch the ball. After 400 training episodes, it's pretty good at that already. So now it's pretty reliably catching the ball and bouncing it back. You can see the score getting higher. After 600 training episodes now, it discovers the best strategy actually, which is trying to dig a hole through the wall and then bouncing the ball up so that it'll automatically bounce around and clear the bricks like that. And the cool thing is it's reliably able to do that. Yeah, which is, I thought is pretty neat. Okay, so yeah, it's getting very, very good. And in fact, so the DeepMind researchers tested this system, the same system basically, with the same hyperparameters, on something like 49 different of these Atari games, each with completely different game dynamics, of course. And the system was able to become superhuman compared to a professional game tester in a majority of the games, and that was quite remarkable. So people didn't know that was possible at the time. Okay, so that was a pretty cool application. Then there's this application that made pretty big news in 2016. There was also from DeepMind, there was this system developed that's called AlphaGo. And this system learned how to play the game of Go, this ancient board game that's played in Asia a lot. It was able to beat the best humans. So here in the picture, you can see Lee Sedol. He's considered to be one of the best players ever in the game of Go. And they developed a system that was using a combination of reinforcement learning directly from basically the representation of an image of the board, and a search technique that's called Monte Carlo tree search. We'll go into that later also in the course. And it became, so it was first trained on some examples of human players, and later on it then played against versions of itself to improve and become better and better. And then they made this tournament against Lee Sedol. It was a big event, and it was a 5-game tournament, and in the end it turned out that AlphaGo was able to beat Lee Sedol by 4-1 games. And this was a big surprise because Go was considered to be a very, very hard problem for AI techniques in general, and people have been struggling with it, with it for a long time, and they didn't consider this would be possible for a long time. So this was, they thought maybe in a decade or so. But then through this AlphaGo system, the progress was sped up so much that it was possible to do this in 2016. And here in the video, I'll play this real quick. You can see Lisa Dahl being very puzzled because AlphaGo just has, okay, now the sound. Yeah, so here he's very puzzled because AlphaGo has done this move, which was very unconventional. It was going against the best practices and known wisdom of the Go community. And it turned out that that move was decisive for the game, actually, also. And this was a really wake-up call for the Go community, because they said, okay, now the system's playing so creatively that we don't even understand anymore what it's doing there, and it's become so good that we can actually learn from it. Yeah, so actually now this the AlphaGo system is able to teach humans new things about Go that we didn't know before. And I recommend, so there's actually a documentary online that about this whole series of tournaments and how they trained the system, and so, which is fun to watch. So I recommend that. It's online. Okay, then I wanted to show you some work from Martin Riedmiller and his group at DeepMind. So this also has a nice connection to Freiburg. Martin Riedmiller used to be a professor here in Freiburg before he joined DeepMind, and also some of my former colleagues, Thomas Lampe, Tobi Springberg, and so on. So I like to show this. And this video shows some nice work where they developed a robot, a system that can teach a robot how to grasp different objects and perform different kinds of manipulations. And what's really cool about this is that they do this in a way with these sparse reward functions that I mentioned. Yeah, so this is a very hard exploration problem, but they figured out a way to generate so-called auxiliary rewards. So the system actually rewards or gets rewards for things that are generally useful, like grasping an object or putting one object next to another. So it's actually also trained on these kinds of tasks, and that generates additional rewards. And by basically bootstrapping on these simpler rewards, it's able to then also solve these very hard exploration tasks, like these sparse rewards, to build these stacks and maybe put them in a different box, like we'll see in a second. So here you can see it's actually building a stack of these blocks. Oh no, okay, it's putting them into this box with a lid even. So figuring out it has to learn open the lid and then clearing the space here, like it's doing there. So that was also very, very neat. Okay, here I want to show you some work that we did that is from the, that showcases some model-based reinforcement learning. So this is going into the direction that you mentioned, learning a transition model, in this case with the Gaussian process regression model. And here again, the system doesn't know anything, the agent doesn't know anything about the dynamics of this card pole system that you see here. It's just interacting with it randomly in the beginning and then recording the sensory data and the actions that it sends, and by that building this kind of a transition model with a Gaussian process regression. And then it uses that in order to perform trajectory optimization with an algorithm called iterative linear quadratic regulator, ILQR. We might speak about it later, and is able to solve this problem in from scratch, basically with a shaped reward function in less than 10 trials. So this is real time. This is not sped up. So in less than in about 2.5 minutes, it was able to learn this in less than 10 trials. Okay. Maybe one more time. No. And then finally, just sorry. How do I switch off the sound? The sound works, yeah. Sorry, just a second. I wonder if we can. Does anybody know how to do this in Zoom so that it isn't transmitted? Or maybe just, yeah. Yeah, let's try that. Output. Yeah. Yeah. Okay. Let's see if I can. Otherwise, we'll skip this, and I just no. Sorry, this is too loud. Okay. Let me tell you what I wanted to show. Okay. So this is a video from my group where we did some inverse reinforcement learning. So this is basically a form of reinforcement learning where you learn from behavior that you observe, and you do imitation learning, basically. So you observe a behavior, and then from that you try to infer what could be a reward function that would explain this behavior. Yeah, so it's different from, someone gives you a cost function, you just optimize the behavior based on that cost function. You try to basically learn the cost function, and then you can again learn to optimize new behaviors on that. And we did that in the context, for instance, of automated driving. So if you think about a person driving a car and you want the car to learn how you drive, basically. We did this in the context of highway driving. You turned off the, okay, then now. But I can't skip forward for some reason. This is weird. Okay, I'll send you the link for this video later. Yeah, so we basically learn from controller that's already trained. That could be a human just driving a car. And from about 30 minutes of training data, roughly, we learn a behavior to overtake other cars in a highway scenario, and also we are able to introduce constraints here, which is, yeah, like I said, not always done in reinforcement learning. So for instance, even though the demonstrated behavior doesn't fulfill the constraints, we can afterwards impose these constraints on the learned behavior. Okay, that's it for me for now. And I'll hand over to Moritz.
Yeah, and I continue with presenting some applications of MPC. I restrict myself to applications that we have done in my team, and they are, for that reason, not maybe as impressive. They are also not about games, but just about some engineering problems. Typically, the timescale is in this robotic frame. I should say that this inverted pendulum that you have shown, I very much like that demonstration. And in some sense, if you would digest what you do, I would even say you do MPC. Sorry for saying that, but you do, so to say, online identification with a model, and then you solve an optimization problem basically to create the feedback controller. IQR is actually solving moving horizon problems, doesn't it? Yeah. So in that sense, it is MPC with a specific sort of algorithm and with online learning. But I mean, this is already one of the interesting things of this course that we maybe at some point you say, but this is reinforcement learning when I present something. Let's see. So just to have a warm-up application, so there's this very widespread application class of point-to-point motions in engineering. You could think of cranes that need to put a load from one point to the other. For example, they could use scrap metal that comes from one heap to another. But you could also think of some things like wafer plotters, which are the machines that move the wafers in silicon processing just a little bit to the left and to the right in order to allow illumination with these lithographic processes. And in the same case, the mathematics of the model is nearly the same. Namely, you have something that when you move it, will oscillate a little bit typically, and that's why humans cannot move cranes extremely quickly. But our aims are always the same. You want to reach an endpoint as fast as possible. So you can say that to a controller, right? Reach the endpoint. Do not violate constraints. So that means don't go over borders. And at the very end, you don't want to have any residual vibrations. And one way to formulate that, as we said already, is MPC, Model Predictive Control, where you use a model to look into the future. We can visualize that by this old car picture that I like to show you. Drive a car by predicting into the future in your head in a prediction model. And this makes you slow down before you enter a curve, for example, because you know you would violate a constraint. If you would drive with full speed into a curve, you would leave the road, and that wouldn't be feasible, so you better brake earlier. And that's what the optimizer automatically does. And of course, a reinforcement learned controller would also do it. And an explicit MPC law is actually very related to a reinforcement learning, I think. Yeah, but typically in MPC, as I said, we do this online. And then we have this optimization problem. I think it's good to get already used to some part of the notation. We use X sometimes for states in control engineering and U for controls. In this course, we will switch this to states S and control actions A. But the optimizer plays with these controls in order to reach the aims, for example, respecting constraints or having a final condition met, as visualized here with the black dot on the right. And after you have finished the optimization, the online part, you use the first control to actually implement it on the real system. And that's what you send to the real system. And that's what one of our PhD students in Leuven did, Liebout van den Broek, who wanted to control a little crane. He did some model identification and implemented the MPC on a little piece of hardware and moved actually the cart motor here. It's like an inverted pendulum, but not inverted. So a bit simpler in some sense. And then the aim was just to move from some points to other points. And I think, did I know? Where do I need to click? Maybe the videos don't work. That's a pity. Yeah, yeah. Maybe go into this. That's what we do, right? Yeah, then maybe let's try that one. That's good. Yeah, I think it works. It just doesn't do. Yeah. Can you show that on the? So we switch presentation. Sorry for that. Is it here or there? No, I have to move that one. So here the controller just gets commands to move to the right or to the left and does it with no residual vibrations. That's one of the aims here. And maybe more interesting is what is happening in the background. And so this is what's happening online. That's a slow motion video of the planner, so to say. That's always planning to compensate for these oscillations by doing counteraction. That's what you see here. Whenever the set point is changed, the optimization plan is immediately changed, right? So just to give you an idea of what's happening in this moving window. I will skip some other applications, but I think I just want to show this because it exemplifies the car example very nicely. This is an MPC running here in Freiburg on a little race car setup. You observe the race car with a camera from the top. There's a little state estimator that knows position and speed of the car and orientation, and then a very simple model allows you to predict where the car would go, and then you just follow a trajectory, the middle trajectory here. And on the top left, you see the planning of the controller. So this is, I think, nicely illustrating what MPC does. This is optimization every 10 milliseconds. I will skip, I think, some other applications, but I wanted to point out that MPC is increasingly being used also for some systems with integer decisions, which are also difficult to control, obviously. In particular, things which have to do with energy storage, like heat storage, battery storage. This is where you have a lot of planning, in particular because you have weather forecasts, which is giving you a wonderful opportunity to build on predictive knowledge. And here's an application that's done by Adrian Bürger, a PhD student who just defended his PhD. Joschka, I think, was in the committee. No, not in this one, sorry. But he is now a postdoc, and he is running actually a solar adsorptive cooling plant in his university in Karlsruhe, which has solar panels to heat liquid in order to cool a building. Yeah, so that's a bit paradox, but there is adsorptive cooling that's possible with heat. And it's a quite complicated nonlinear system with lots of states, 39 states, 6 continuous controls, and 2 binary inputs. Namely, you can switch on this cooling machine or some free cooling, as it's called. And so he was running this machine for some time. I think we have here some plots from September 2019. So here you see the ambient temperature on the top plots, and this is real experimental data. What is maybe more interesting are the integer decisions at the bottom. So this machine is sometimes switched on and off at times which a human wouldn't be able to decide in order to exploit optimally the internal storage tanks and the also the storage of the building and to build on the weather forecast. There's a lot of integer decisions, and that's quite challenging for the numerics combined with the nonlinearity, and that's why I wanted to show this. This time scale is about 2 minutes sampling time, much slower than the other, but you have also harder problems to solve. And yeah, I think I skip nearly all other applications for the sake of time. We will put the videos online. Some robots, don't worry. Maybe one video I still wanted to show, and that is this one, because it nicely illustrates what is happening in MPC with the state estimator. So this was done by Milan Vukov, who did his PhD on this setup where we actually swing an airplane on a cable around a little setup, and you see the setup in the back. So that's, so to say, the real world. And in the virtual world, you see the, as we would call it nowadays, the digital twin, right? That was basically the state estimate that's always observing the system. So you see on the right screen the optimizer, the moving horizon estimator, the estimator. And at some point, controller is switched on. It's not extremely impressive trajectories. I would say the main point here was to show that it's doable in real time. It's about 10 millisecond sampling time with all these things together. And here you see that this plane is nicely stabilized and controlled to different set points in this setup. And the last application is on the other side. Here we have only 250 microseconds for each optimization problem, so it's quite fast. It's still doing online optimization, and this is applied to reluctant synchronous machines, which are a special kind of motors, which are quite nonlinear. So there's a significant nonlinearity in the magnetic flux equations here that I don't want to discuss, but there is an online solution, and if you let one of these motors, which is actually the black motor, run against a test motor, which is this orange one, then you can do some step changes, starting, stopping, changing the torque quite quickly and quite reliably with MPC. And you can beat, particularly when you're at the boundaries of the operating region, when you are, so to say, close to constraints where the power is nearly at the maximum and so on, you can very reliably beat other controllers, which are like well-tuned PI controllers used nowadays. And so that's one of the, let's say, faster applications of nonlinear MPC that shows you a bit the spectrum of where MPC is used nowadays. It's engineering problems, typically slower timescales in chemical engineering, a bit like the solar plant that I mentioned before, but nowadays more and more for fast processes like mechanical and also electrical systems. So I think this is where I wanted to stop this introductory talk. We will have some time of interaction now in a break, and we continue in, I would say, 10 past 10. Okay, thank you.